For the emission spectroscopy experiment, we are only doing part A. We are not doing part B. Part A has us working with hydrogen. So, being hydrogen, we can use the Bohr model. The Bohr model, recall, is delta E is equal to negative 2.178 times 10 to the minus 18 times 1 over n high squared, or n final squared minus 1 over n initial squared. This equation 1 is another way of stating the Bohr model equation, where n low, n high have replaced the n final, n initial, and instead of delta E, which is equal to the energy of the photon absorbed or emitted, this one has 1 over lambda. Recall that delta E is hc over lambda, and so that's the agreement between those two equations. In this equation, given that we have not delta E, but we have 1 over lambda, we don't see that number, the 2.178 times 10 to the minus 18. Rather, we see R sub h, and R sub h is 1.097 times 10 to the 7th inverse meters. That's the Rydberg constant. That is not R, the universal gas constant. Same symbol, but very different constant. Okay, so part A, that has us working basically with this part of the introduction. So for the experiment, what we're doing in part A is setting up the tube of hydrogen. You'll see that in the experiment video, and a spectrometer, and we are getting the spectrum of hydrogen. The spectrum of hydrogen is given to you in Canvas, and it has 4 peaks in the visible spectrum, and they are at the highest energy one would be at the shortest wavelength, 410 nanometers. That is the 6 to 2 transition. The next peak is at 434 nanometers. That's the 5 to 2 transition. The next peak is at 485 nanometers. That's the 4 to 2 transition. And the highest energy peak is at 656 nanometers. That's the 3 to 2 transition. So with that, we then can go to the report and start talking about the analysis. So there are 2 graphs you'll see in Canvas. Graph 1, or the first one, is the hydrogen emission spectrum graph, and it's the one that I just talked about with the 4 peaks, intensity on the y-axis, wavelength on the x-axis. And you, of course, are not going to print that or submit it or anything. It's given to you. The second graph is the graph that was made following the analysis that we will look at when we look at the results, the report sheet. But to see how the information was determined, go to this information here about graph 2. Okay, skip the pre-lab. So here's our report. So for part A, for this first table, then we would write the 4 wavelengths here. We write the transitions here. We just talked about those. You will notice that all of the transitions are from a higher level to 2. The third column is referred to as the n expression. So it's 1 over 2 squared minus 1 over n higher squared. So you would calculate that based on what the n high is. The next column, the wavelength, you're converting from nanometers to meters, 10 to the minus 9. The last column is to take the inverse of those wavelengths. Now we are ready to use that. Let's go way back to the top. We're ready to look at that equation from the very first page, the Rydberg-Balmer equation. Okay, this equation 1. So what we have is values for 1 over lambda. We have, and that will be plotted on the y-axis. We have values for this n expression, 2 squared minus 1 over, so 1 over 2 squared minus 1 over n high squared. So we will have values for that. Our only unknown will be the Rydberg constant. So we're going to plot 1 over lambda on the y-axis versus the n expression on the x-axis. We will see that that data looks linear. We fit it with a linear function, and the slope of it is equal to then RH. So that's what's being done in that reports table. Let's see, that's in the calculation part here. So the Logger Pro, remember Logger Pro is our graphing software. Okay, so the results. So from the graph number 2, you will put the slope, you'll put the y-intercept, the correlation coefficient, and then you'll write out the equation, which will look like what's on the y-axis equals the slope times what's on the x-axis plus the y-intercept. The y-intercept is pretty close to 0, so you can actually discard it. Actually, it's not so close to 0, but in comparison to the huge slope, yes, it becomes. Okay, so from this, answering number 2, what is the value for the Rydberg constant from your experimental data? And then you do problem number 3, which is having you compare the experimental one with the accepted one. You can skip this part B here. And then for the questions, this one is called question 6. Do that one. So you are using equation 4, which is the usual equation you're used to, and you're putting in values for n, and you are converting from joules to kilojoules per mole. So that's what's needed for this table, question 6. Question 7, once you've got these energies here in number 6, you will put them on this hydrogen atom energy level kind of like diagram here. So plot them appropriately. You only have to work on the hydrogen atom part of question 7. And you can skip the rest of the questions. So once you're done with that, make your scan, PDF, and submit it.